Hey everyone, we're here with Sean from the Electric Coin Company. He'll be doing a talk on Halo 2 and SNARKs without trusted setup. And once he starts talking, can you guys just confirm you can hear him?
Hello, Sean here. Let's see if it's working. Testing. Hello. Can you hear me?
Yeah, I can hear you.
Okay. I'll just go ahead. I guess it's working. Okay, so yeah, my name's Sean Bowe. I'm an engineer and researcher at the Electric Coin Company. Our company sort of created the Zcash cryptocurrency, and for the last 4 years, we've been shepherding it with the help of a community and the Zcash Foundation and a lot of very talented cryptographers. So today I'm going to be talking about Halo 2 and my view of the current state of SNARKs without trusted setups. And I think what we have now is really exciting, and there's a lot of exciting years ahead. So just to give a little recap, as far as Zcash is concerned, our original launch was in 2016, and we called it Sprout. And when we launched with the first ZK snark in production. It was a ZK snark called BCTV14, and it's kind of a complicated protocol, and it's built using these special elliptic curves called pairing-friendly elliptic curves, which are kind of like normal elliptic curves, but they're a little weaker in their security so that you can do some cool stuff with them, but not weak enough that they're totally useless. They require some stronger assumptions, but one of the kind of most well-known limitation is the fact that it requires a trusted setup. So as part of our original launch of Zcash, we set up this ceremony, which used a multi-party computation, where 6 people got together and, communicating over air-gapped network machines, they would collaboratively construct this thing that we refer to as a structured reference string. And this structured reference string, or SRS, is required to create and verify these proofs. And if the SRS is generated by an adversary that has total control over it, or if this ceremony is compromised, if all 6 participants collaborated or were compromised, then they would be able to create false proofs. And so they would be able to not violate anyone's privacy in Zcash, but they would be able to inflate the money supply and create just infinite amounts of money if they want. So that's bad. So we needed to create a robust ceremony to create this structured reference string, which we did. Now, the reason why we use these strong assumptions and we relied on these trusted setups was, at the time, there was really no other option. We needed a proving system, a ZK snark, which was super efficient at reasoning about very complicated relations. In the case of Zcash, we needed to prove membership in a large accumulator, in our case, a very large Merkle tree of depth like 28 or something like that. So in the original protocol, we used SHA-256, and SHA-256 is hard to reason about in these kind of proving systems. But in any case, these are very complicated statements. And the reason why we did this was for strong anonymity. So like I said, there are some limitations. We required a trusted setup. And there's a lot of people that don't like trusted setups for a variety of different reasons. There's ideological opposition to it. And there's also a really good reason, which is that it adds complexity, which kind of feeds into the next point. There was actually a flaw in the paper in the ZK snark, particularly in the way that the setup is supposed to work, where the actual SRS was broken. So we want to avoid trusted setups for a lot of reasons, including that. In the original protocol, like I said, we used SHA-256, and we had to reason about that. That made it really slow. It wasn't entirely the proving system that was slow, but the proving system, BCTV14, was pretty slow as well. And the protocol lacked some scalability features, which I'll get into in a little bit. So a couple of years later, we deployed Sapling, which was a network upgrade, which used a new proving system, kind of the bleeding edge proving system. This slide should say Sapling in 2018, not 2016. Sorry, but Grout 16 was extremely efficient. 3 group elements. So you have these proofs that are less than 200 bytes in size. We created this notion of an embedded elliptic curve and used it to build these primitives like Peterson hashes and all this other stuff to replace SHA-256 in the protocol, and did lots of cool optimizations that are too involved for me to talk about here, but those helped improve the performance. And to improve upon our original launch of Zcash, we developed a multi-party computation protocol specifically for Grot16, which took advantage of some of the properties of Grot16 and also some new ideas, and made it so that it could scale to hundreds of participants. And so we did this huge ceremony with lots of contributors all over the world, where like 100 people would have to collude to compromise the ceremony. So it was much more robust. So all these performance improvements we did in Zcash were incredible. They allowed us to actually have these proofs be generated on your phones. You can make shielded to shielded transactions in Zcash on your phones now. That was impossible before. These proofs used to take like 40 seconds to generate just on their own. So the proving system is much more efficient now, and obviously we've avoided some of the flaws by moving to a simpler protocol that's more well studied. But we still have a trusted setup that we want to avoid for a variety of different reasons. And again, some scalability features that I'll talk about. So we did a bunch of research at the Electric Coin Company for a couple of years, and we stumbled upon some ideas that actually are really incredible kind of breakthroughs in how we achieve both creating zero-knowledge proofs without a trusted setup and also building these primitives which use recursive proof composition. So last year, we announced Halo, which was this kind of the culmination of this effort. My co-authors, Jack Grigg and Dara Hopwood, are at the Electric Coin Company as well. And before we announced Halo, there was no real way to do, no one knew of an efficient way to do recursive proof composition that didn't require these gigantic pairing-friendly elliptic curve cycles that were like 700 and some odd bit pairing-friendly curves that required trusted setups and so on. So Halo was able to move us from these gigantic, expensive curves to simpler, smaller curves, kind of the same size as SEC-P256K1, that didn't require strong assumptions. We're just using the discrete log assumptions and similar things like that, random oracle model. And we didn't require a trusted setup, which was all great. So the basis of Halo is this inner product argument, which comes from a paper that Bulletproofs eventually built on top of. And we can take this sort of specialized variant of this inner product argument and build what's known as a polynomial commitment scheme. So the idea is I have a polynomial, a univariate polynomial, and I want to commit to it. So we have this vector G bold G, which is just a vector of random group elements. And we compute a Peterson vector commitment to the coefficients of the polynomial that we want to commit to. And we have another vector B, which is it's the power vector of X, some X in the field that you want to, basically the inner product of A and B is the evaluation of that polynomial at X. So in a polynomial commitment scheme, you want the prover to be able to commit to a polynomial based on a vector commitment to the coefficients, and then prove that they evaluated it at a particular point of the verifier's choosing. So in this case, X, and so the prover will supply V, which is allegedly the inner product of A and B, and we will begin this argument based on the kind of a specialized form of the inner product argument, where we initialize for the kth round, where k is like the log of n, we initialize pk as the original commitment plus we sample some random u in the group, and we take v to the u and add it to that. And then we do this recursive protocol, which starts like this in the kth round. So in the kth round, what we do is we actually split the vectors a, b, and g into halves. And then the verifier samples a random challenge And then we compress the vectors by taking, for example, for the A vector, we take all of the low halves of A and multiply it by the challenge. And then we add that corresponding vector to all the second half of the A vector multiplied by the inverse of the challenge. And we do the opposite for the B and the G vectors. And so when we do this, we can actually rewrite an equation of the same form as PK using these compressed vectors. So you can see on the bottom there that we've essentially rewritten the original vector using those modified vectors. And so what we can do is we can run this protocol recursively. So in the k-1 round, we do the exact same thing, and to compensate for the inverses, and we multiplied the so the prover will provide these commitments to the low and high halves that are using the high and low halves of the G vector from the previous round. We can just keep doing this over and over until we end up with a vector of size 1. So the claim just gets much simpler. To cut the story short a little bit, basically in the very end of the protocol, it's much more complicated than what I'm describing, but at the end of the protocol, the verifier has to compute these values G, which is an inner product of this vector S with the random group elements G, bold G, and also this B0 or B, which is the inner product of S and B, where S is this kind of weird-looking structure that's based on, it kind of takes its form based on the nature of the, it's like a Boolean counting structure that's based on the nature of the fact that the collapsing is happening recursively in the protocol. But it turns out something that we noticed in the Halo paper was that if we define this polynomial G, which actually has a really succinct representation, we can evaluate it at arbitrary points very efficiently. We actually can compute B0 very efficiently using that representation. And another thing that's really interesting is that we can actually compute G as the commitment to that polynomial with X as the formal indeterminate. So this comes in handy when we're building SNARKs, because polynomial commitment schemes form the basis of many modern SNARKs. So if we have a polynomial commitment scheme, a succinct polynomial commitment scheme, and what we call a polynomial IOP, interactive oracle proof, that has various certain properties, we can create a SNARK. So one of the first polynomial IOPs is one that we used in Halo. Actually, when we announced Halo, when we were building Halo, there wasn't any other ones that had been released recently in the literature. Very quickly after that, last year, Marlin and Plonk were announced. And Plonk actually is what we'll be using in Halo 2, which I'll talk about in a second. So there's something important about this thing I mentioned before about the fact that this G value that the verifier has to compute is a commitment, happens to also be a commitment to this polynomial that we can evaluate very efficiently, is that imagine that we have two proofs, pi1 and pi2, and both these proofs are using some polynomial IOP and the polynomial commitment scheme I just described. So the verifier, if they wanted to accept each proof, they'd have to compute a G value for each proof, which I'll call G1 and G2. Instead, what they can do, what the verifier can do, is it can have an untrusted helper provide G1 and G2, or what it claims to be G1 and G2. And so the verifier can go on and accept the proofs, and then it just needs to be assured that G1 and G2 are correct. And so what will happen is the verifier will sample a random value Z and X and ask the prover to open G1 plus Z times G2. Again, these commitments are linearly homomorphic, and it'll ask the prover to use the polynomial commitment scheme argument that I was just describing before, which is like a subset of the inner product argument, to open it at this random point X. And the verifier can evaluate the expected opening very efficiently, sublinear time in the degree of the actual polynomial. In fact, the product of the amount of commitments you have times logarithmic in the degree of the polynomial that you're opening. So we can do this with more than just 2 proofs. We can do this with as many as we want. And effectively what we're doing is we're amortizing away the linear time work of many proofs so that you only perform that linear time work for a single batch of proofs. So where this comes in handy is in recursive proof composition. So in recursive proof composition, we want pi k to be able to say that that we know a previous proof pi k minus 1 that we've checked it, and in order to do that, of course, we have to compute this gk minus 1. But that's linear time, and so we wouldn't be able to create a circuit that converges to a finite size if we were to do that. To avoid this, what we can do is we can have the prover witness gk minus 1, and then take gk minus 1 and also the challenges that purportedly were used to derive it as a public input. And as a consequence of doing this, the next proof, so pi k minus 1, would have the problem that it would need to check gk minus 1's correctness, and also it would need to, the prover would need to witness gk and bring that in as a public input. So we've only kind of partially sidestepped the problem. To avoid this, what we can do is we can run that amortization idea inside of the circuit. And like I said, because of the marginal cost is sublinear in the degree, this amortization process is really efficient. And so we can take the G for the G element that needs to be computed and witness it for the proof that we're checking, and also the public inputs that we're checking, and then amortize it away and bring that out as a public input. And we can keep doing this over and over and over, and it allows us to achieve arbitrary depth recursive proof composition. So there's a generalization of this very idea called an accumulation scheme by these authors that have written this paper. And so there's been a couple talks that might be of interest to people in the audience. I did a ZK Study Club talk that goes into depth on how accumulation schemes work. And there's also a talk by Nick Spooner about how they work as well, which is really nice. Good talk. So what is Halo 2? Well, Halo 2 is our attempt to take the original protocol that we developed last year called Halo and replace it internally with Plonk. Originally, we used Sonic, of course. So we want to create a very highly optimized open source. You can freely contribute to it, fully documented and specified and security proofs and highly tested implementation that can serve as the basis of the next generation of zero-knowledge proofs that can be used in Zcash. And of course, Halo 2 doesn't have a trusted setup and supports recursive proof composition, which gives us a lot of, which offers a lot of, offers us the ability to do these really scalable variants of the Zcash protocol. It allows us to improve block verification. It allows us to aggregate transactions together. All sorts of different scalability bottlenecks that might show up in Zcash, we can use Halo 2 to address those. And another thing that's important for Halo 2 or for Zcash, and might be important for many other protocols, is generating multiple proofs at the same time and having a cohesive API for doing that securely. So that's another one of our important components of Halo 2. So just to give a sneak peek into the performance of what SNARKs performance is like without a trusted setup today, it's really amazing. We've been working with this hash function. It's based on the Peterson hash called Sensimia, which uses lookup tables, uses a protocol kind of like Plookup to perform fast coordinate lookups. And so we can actually have a 32 depth binary Merkle tree membership of an accumulator proof that verifies in 30 milliseconds on a single thread, which gets so close to the performance of pairing-based SNARKs, which is awesome because it doesn't require trusted setup. And the proofs aren't that much larger, and they're actually quite fast to generate, but obviously it depends on your hardware. Certainly faster than the Grot16 proofs that we're creating today in Zcash. So we're actually going to be using this hash function to create a proof of concept Sapling-like protocol for Zcash, which doesn't require a trusted setup, just to show just how efficient SNARKs without a trusted setup are getting. It's starting to become so competitive that there's very little use for protocols that use trusted setup as time goes on, which is awesome. So like I said, SNARKs for really complex relations are becoming super efficient, and we're approaching with Halo 2 and similar protocols. We're approaching the performance of what trusted setup based SNARKs had 4 years ago. So we're catching up pretty quick. Halo 2 is our attempt at building something that we can use in Zcash in production, something that's tested and well engineered and well specified. So thanks for listening, and I'm happy to take any questions if there are any. So actually, let's see, I'll go over here and see if I can find the questions in the, if there are any questions. I'm happy to answer some. I don't see any. It looks like Dara is actually answering all my questions. Thank you very much, Dara. Well, if there aren't any questions, then I'll just wrap up, I guess. Thanks for listening.
Cool. Thanks, Sean. This is really great. We're going to transition to the next talk. Thanks. So everything is live right now. You can actually watch all the recordings right after. Sean, I think you're still here. I think someone just asked a question. Does Halo 2 help with sharing, and if so, how?
Does Halo 2 help what?
I don't know. It says help scaling. And
yeah. So the fundamental ability to be able to aggregate proofs together through recursion, that helps address many different kinds of scalability bottlenecks in so many different protocols. So, for example, you might have two transactions in transit on the network. I like to think of a transaction in a Zcash-like protocol as having a big proof blob and a small data blob. And the data blob is just a bunch of random data, and the proof blob takes a lot of time to verify. If you have two of these transactions or two of these proofs or whatever, you can use recursive proof composition to sort of merge their data blobs together. This is kind of the way I think about it. So just that alone allows you to sort of aggregate transactions and reduce their space and also their time to verify. And you can do this not only at the transaction level, but you can also do it at the level of blocks and things like that. I just noticed my video is off. Sorry about that. So yeah, Halo 2 definitely helps with scalability. Anything you'll see these other protocols that use that have what are called succinct blockchains. That's not really a scalability thing. It's more of just like helping the environment and things like that, which is also really good. So it helps in many different respects.
Awesome. So I think that's pretty much it. We can transition to our next talk now. Thanks again.
Cool. Thanks.